Euclidean Geometry, Rider 10. So there's my usual reminder to you about thought processes in doing geometric riders. We have a circle, two tangents, sorry it doesn't say it there, but they are in fact tangents, a diameter with a center O, and we are told that E is the midpoint of SP. Now, I always recommend that you don't mark off everything you can see in a diagram because it can just confuse you. But there are certain things that it's worth marking off just in case you miss them later. They're funny little things like angle and semicircle. Then we have a chord theorem. Line center to center of chord from the center of the circle. Right? Midpoint, that's the chord theorem. And then finally, radius tangent, we have the angle between a diameter or radius to a tangent, 90 degrees. That will be useful having those sitting there right in our face. So let's look at the first one. Prove OE parallel to RS. Now there we are straight away. If proving something about lines or shapes, ask what if it is so? So what if OE is parallel to RS? Well, S2 would equal E1, corresponding angles, parallel lines. And they are equal. They're both 90. So we can start our first section of the proof. S2 equals 90 degrees. Angle and semicircle. EP equals ES given, therefore E1 is 90 degrees, chord theorem. And therefore we have E1 equal to S2. And that makes OE parallel to RS because the corresponding angles are equal. Now we need to prove two triangles similar. There they are marked in the figure there. And I suggest you always, in the interest of not waiting for geometry to come to you, you list the angles, decide which angles are probably going to be equal to which angles, and then you go through and try to work out why. So S3 equals O1. S3 equals O1. E3 equals P there. And the remaining N1 equals N2. Well, we say, what is S3 equal to? Remember, this is a tangent, that's a chord. So S3 is equal to R. That equals that. Know your theorems. And now we ask, is R equal to O1? Is R equal to O1? And of course it is, because they're corresponding angles. So we have that, so that's okay. Next, E3 and P1 and 2 are equal because they are 90 degrees each. And of course the final pair by angle sum triangle. So let's do the proof. 1. Now we do our little mini proof inside to prove that S3 is equal to O1. S3 is R, tan chord, R is O1, corresponding parallel lines. Therefore S3 equals R. 2. Both E2 and P1 and 2 are 90 degrees, and that is proven. N1 equals N2, angle sum triangle. So we have the two triangles similar. Remember to state them in the correct order. S equals O, E equals P, and N equals N. N1 equals N2. From there, we can now have a look at the third part. Pn squared equals En times On. So if we take that, there we are. That's the relationships given. Now, all I'm doing is I'm not waiting. I'm looking to see. Now, if you have a look, Pn, there's a Pn, but they're not two Pn. So that could be a problem. There's an En, yes. There's an On, yes. So, in fact, everything's involved with these two, not that one. So we can take that one out, and there we have it there. Now, what are we going to do about the Pn? We need two Pn's, and there's only one. So we look at say, what is Pn equal to? If we look at this, oh, hang on, Pn is equal to Ns. Sn, there it is there. So there is our working. We know that Sn equals Pn, so therefore I've changed the Sn to Pn. And now we have it. So let's prove it. There we are. Similar triangles proven, just for the fussy marker, and come straight from there. Pn, second third, must go over second third, equals On, first third, and must go over first third Sn. But Sn equals Pn, tangents from a common point. We haven't used that much in these riders. And therefore I've now substituted Pn instead of Sn, and that gives us what we want to prove. Right, we're looking at the next one now. Pe squared equals OE times En, so I get it into the proportion form to be able to look at, so I can do a vertical or horizontal test. Going vertically, I get PNE OEP. Yes, those are feasibly similar because that angle there must be a right angle, and so I think we've got it in fact. So let's have a look. E1 would equal E4. Well, yes, they're both 90 degrees. O1 would probably equal P2, so we start our thought process and say, well, proving two angles equal, take one and find what it is equal to. So what is O1 equal to? What is O1 equal to? Now remember we have the parallel lines, so O1 equals R. So next question to ask is P1, P2 equal to R? Of course the answer is yes. Tangent, chord, angle subtended, know your theorems. Yes, tan chord. And of course angle sum triangle for the third one. So we can prove those triangles similar and go on to prove this relationship. So in triangles, E1 equals E4 90 degrees. I'm sure in earlier days, well not that one, in the next one, you might say, well, how did they know to do this little mini proof? Well, this thought process takes you there to do a mini proof. So O1 equals R, corresponding angles, parallel lines. R equals P2, tan chord, and therefore we have O1 equal to P2. And therefore what's left equals what's left, angle sum triangle. Stating the similarity, remember O is equal to P, E1 equals E4, and P equals N. Therefore, and I'll take that straight from the similarity. Now have a look here. I want PE squared, so that means I want a PE on top and a PE below. PE from the first and PE from the second. Now if I have a PE there, that's second, third. Below must go second, third. The PE below from the second triangle, it's first, second, therefore first, second must go above. And that goes straight into what we have to prove. Now, when we look at this third one, question 3. In these questions, when you have that sort of thing where it doesn't quite look standard, it's usually always algebra. We have a look here. There are 1, 2, there's 2 sides, 3, 4, 5, 6 sides involved, and we need 8. So it's got to be algebraic. So what I'm going to do is I'm going to observe, compare this to what's already been proven, and you should notice that. Well, have a look now. I've changed the color here so you can see Pn squared. Where you see a Pn squared, where do we see a PE squared? Aha, there's the PE squared and Pn squared. So to get that over that, all we do is divide these two and hope that that works out. So let's have a look. Pn squared equals En times On, proven, and PE squared equals OE times En, proven. Now we're going to say 1 over 2. So therefore that over that equals that over that. Now that's quite useful. You notice we have an en which cancels, so we end up with on over oe. Now we don't want on. In fact, we do want on, but we don't want rs. We want oe. So we have a look and say, well, what is oe? Let's say it the other way around. Hey, we don't want OE, we want RS. What does OE have to do with RS? Well, have a look here. You can't use proportional intercept theorem because proportional intercept theorem doesn't use the parallel lines. But if you look at these triangles here, there are two ways you can look at it. If you've done midpoint and intercept theorem before, you can do it that way. But if you haven't, you could just say, well, this triangle here is similar to that triangle there. You can see corresponding angles, and common. So therefore, OE over RS equals PE over PS. And PE over PS is a half. So therefore, OE is half of RS. So instead of OE, I'm going to write half RS. And now when you're dividing by a half, you multiply by 2, and there we are, we have what we have to prove.